Hello friends, welcome back again. Today I want to ask you one question. Are you feeling any problem between what ductile materials are and what plastic materials are? Are you still feeling some confusions in stress strain curve? Well, in this video I'm going to explain you every sort of detail about the stress strain curve of a mild steel bar, and we'll be talking about the different kinds of materials like elastic, plastic, ductile, brittle materials, and obviously the tests which we do in the laboratories to determine the physical properties of materials. We'll look into that as well, how those parameters, if we vary those parameters, how they are going to affect our material properties. So let me basically explain the types of materials. Basically we have four materials. Let me write over here. Four types of materials: elastic materials, we have plastic materials, and we have ductile materials, and lastly we have brittle materials. So all of you must be having some sort of knowledge about these materials, and for just revision purpose I will just explain them in brief. About elastic materials, we know that if they undergo some deformation, they recover it, and as the force is removed, if for example I have a elastic material over here, for example if I am loading it this way, and it will induce some deformations in this material, and after the removal of this load P, the deformations will they will come back. It will regain its original position. Maybe it elongated to this extent, and then after the removal of loads it will come back. So these are what we mean by elastic materials. So what plastic materials are? Plastic materials, if a material does not regain its original position on the removal of external loads, it's called a plastic material. Now what about ductile materials? Ductile materials are simply those materials that cannot undergo a considerable deformation without rupture. So ductile materials are something different. Elastic and basically what my aim was to differentiate between these materials and these materials. We sometimes refer elastic materials as ductile materials, but practically they are different. Ductile materials are simply those materials which undergo a considerable deformation without rupture. If a material can be drawn into wires, it's called a ductile material. So on application of load, if my material will change, it will get deformed. Okay, there will be obviously laterally the dimensions will decrease, and if longitudinally we are increasing the dimension, I'm drawing this metal into wires, so the thickness of the member will reduce. So that's what we mean by ductile materials. And about brittle materials, as all of you know, they cannot go any deformation. For example, if you have glass, you have chinaware, when some external load is applied on brittle materials, the force acts on it, but it fails. It fails to produce some deformation in a brittle material, because brittle materials have that sort of chemical composition. They will not show any sort of deformation in them, and they will then regain their original position on the removal of load. It doesn't happen with brittle materials. Brittle materials, they will rupture. They will rupture suddenly. For example, if I have a cube of glass, for a glass material, and I'm loading it by somehow externally, it will not induce any deformations in it. There will be no deformations in it. It will rupture. It will rupture at its weakest plane, whichever it may be. So this is what we mean by these materials. But basically today we'll be dealing about the tensile test of a mild steel specimen. We'll be drawing the stress strain diagram, and we'll be talking about the UTM as well. So let me rub this first, and then we'll move towards that. It's not working. Let me use this. I hope everyone is fine back home. These lectures are very important for all of us in this corona period. We have to stay at home and we have to be safe to keep our generations alive. So let me go to the stress strain diagram of the mild steel specimen. For example, let me write over here. Firstly, we have UTM, Universal Testing Machine, where we actually do this test. Where we can actually see when we increase the stress and what about the strain in a mild steel specimen. And up to rupture, we have extensometer over there, where those clips maybe like this. They are actually fitted in our specimen. If this is the mild steel specimen over here, and we have this rod, okay, and here again we have this extensometer where we fix this. So this much of length is called gauge length. Actually, what we do, we induce the stresses, or we apply the force, tensile force, due to these extensometers in the UTM, and then we see the behavior of this gauge length. And it's a software-based thing that we do. You all must have done this test in your graduations. So basically, what I'm going to do is, we are actually drawing a stress strain curve of the mild steel specimen, and we'll be actually trying to know what those points actually denote. Let me do it this way. For example, if this is the stress axis and this is the strain axis, this is my stress axis. Actually, basically, we convert these things into stress and strain. We have force actually when we apply the force in the extensometer. Okay, we convert that into stress. So actually, the UTM gives force to the member, but that force is converted into stress in the software. So actually, if this is my original specimen with some dia, and obviously the cross-sectional area is pi by 4 d square. If this is the dia, of the specimen. So this is my area, and while we are drawing, we actually use engineering stress. Which is actually the force at any point divided by the original cross-sectional area, pi by 4 d square. So basically we use engineering stress while we calculate this. We can also use the true stress as well. True stress is simply the force at any point divided by instantaneous cross-sectional area. Instantaneous, maybe it may be either smaller value than the original or the larger. It will depend upon how I am applying the loads, if there is tensile load or if there is compressive load. Instantaneous area. So this will be my true stress. Force divided by instantaneous area. Engineering stress will be force divided by my original area of the cross section. So we'll be drawing the engineering stress over here, engineering stress diagram, and strain. So what I said, the extensometer actually that gives you force, and the strain, how we calculate that, we actually get the delta L, the change in the length, the change in the gauge length of your specimen. We calculate delta L and we divide it with the original gauge length in this stress strain curve that we are about to draw. So let's move ahead. Basically, when we plot the stress strain curve of the mild steel, we actually get a straight line initially up to this point. So this point A, let this point be O, let this point be A. This point is the proportionality limit. Up to this point, your stress and strain are directly they are linearly proportional to each other. So basically, the Hooke's law that says the stress is directly is equal to Young's modulus into epsilon. What's epsilon? Epsilon is your strain, and this is Young's modulus. Strain is dimensional less because its value is the change in length divided by ordinal length or whatever you have, width or height, and the E, Young's modulus. Its units are actually the units of stress, maybe Newton per meter square or whatever units you use, but the units of Young's modulus and stress are the same. Now this point, the point A, it is the proportionality limit. And what do you mean by proportional limit? The stress up to this point is directly proportional, it's linearly proportional to the strain. So we get a straight line from O to A. And from A, we have another point, nearby point B over here. And it's slightly curved up to this point B. And the graph shows that there's a curved variation. It's not linearly. So up to this point, we have up to from O to A, our Hooke's law. I'll write it here. Let me write here. O to A, Hooke's law is valid. Up to A point, Hooke's law is valid. But from A, we get a curved line, we get a curve, and it's not linearly proportional. The stress is not linearly proportional. You see at some other value of stress, we are getting more strain. So basically, up to this point B, this is called the elastic limit. Now, what we mean by elastic limit is that if from point B I am going to remove the loads, I am going to remove the stress, whole of the strain, this much of strain, whatever it may be, maybe it's the elongation. We sometimes we say it will depend upon the material properties, obviously, but mostly books will write maybe 2% elongation, not strain, 2% elongation up to this point, up to elastic point. We have 2% elongation, and that 2% elongation will that will wash off. There will be no elongation if you are removing the loads. So that is the significance of elastic limit. But up to elastic limit, Hooke's law is not valid. Hooke's law is valid up to A point only. Now, when we stress it further, when we are providing more stress to our mild steel specimen, we get one more point over here. This point C. This is called upper yield point. This point is proportionality limit. I hope you all will be drawing it. So this point, upper yield point, this signifies that the yielding has started. The yielding of the specimen has started. So basically, the yielding starts from this point C, and just if you are increasing the stress value, you'll just after this point you will see at lower stress values the curve will behave like this. There will be ups and downs, but at a minor scale we show it straight. So we call it some plateau. So what basically it is, whenever we are going above the upper yield point on the mild steel specimen, we'll see there will be reduction in stress and strain will try to increase itself. So this is where the yielding starts. This point is called lower yield point. Yield means when you are getting something. So we get the strain over here. At constant value of stress, you'll get the strain. Okay, you'll get a lot of strain. So after point B, for example, point B to C, the upper yield point, and C to this D point. This is the lower yield point. So this lower yield point is very important because it's very difficult to determine the upper yield point. There's slight difference between upper and lower yield, but at lower yield point we are getting a lot of yield. So lower yield point is very easy to determine than the upper yield point. So actually lower yield point has more significance than the upper yield point. Okay. So basically, after then this mild steel specimen shows a different behavior. From this point, where the yielding has stopped, there will be beginning of strain hardening. The material will try to become more stronger again. It will try to adjust the molecules. So where this is the point E, where the strain hardening starts. Strain hardening, the material gains more of its strength due to its intrinsic properties, due to its intrinsic molecular composition. So you have to increase the stress now. You have to increase the stress to get strain. So you are getting strain. You are actually trying to make this mild steel specimen to fail at some point. You won't calculate how it is going to behave under these increment of stresses with time. So basically now the material is trying to gain the strength. You have to apply more stress to get more strain. So basically it will behave like this now. And you'll get a point over here, this F point, where you have the maximum strength, and you call it ultimate stress point. You call it ultimate. This is the point where your specimen has the highest strength. It can resist highest load. So you have to see the behavior. If practically, for example, in an earthquake, when there is the yielding of steel bars, for example, in under reinforced sections, this yielding of the steel bars occurs first before the crushing of the concrete takes place. So if you want to visualize over there will be yielding, and then again there will be strain hardening if there is more stress due to those earthquake loads, and after that your specimen will be having more strength. And at that stage, that will be called as ultimate stress point. And if further it is loaded, it will break. Now it will break because the stress value, at lower stress values now, you'll be getting more and more strain, and up to this point, maybe this point G point. This is where your specimen breaks. This is breaking stress point. So this is your breaking stress point. See, this is how this mild steel specimen behaves under variation of stresses. So this is the point. Now, for example, if I have a material like aluminium, in aluminium we don't have these prominent upper and lower yield points. For that we use offset method. Offset method, if for example, I will show you over here in this curve. If for example, this aluminium has a curve like this, so you don't have those prominent, you want to see the yield strength of the aluminium sample. So for that you have to do one thing. You have to go to 0.2% strain. You have to draw a line. If this is the proportional line up to this point, you have to draw a similar parallel to this line. You have to draw a line, and whenever it cuts at whatever point it cuts the curve, that will be your yield stress. Yield stress of this specimen. So offset, we use offset method at 0.2% strain. Now, I want to tell you one more amazing thing. If, for example, if you have we're using engineering stress in calculating all those points. If you will be interested in using the true stress. So at this point where the necking formation starts, from this point the necking formation starts, there will be a reduction. Your specimen will be like this at some point in it. It will be like this. There will be a lot of reduction in the cross-sectional area. So if you are using true stress, your cross-sectional area, that is P by instantaneous cross-sectional area, this instant cross-sectional area is very less, so you'll be getting more values of stress. So if you are using the engineering curve, that will behave like this. That will be going higher and higher, giving you the higher values of stress. Due to this, when you are using the instantaneous cross-sectional area, because the cross-sectional area is getting reduced at every point. So this was about the stress strain curve of mild steel bar. Hope you will have enjoyed the video, and we'll be actually uploading more information on this stress strain curve, which will be used in the SSC JE exams, because they actually ask the typical points about this curve, maybe some numerical data, and we'll be uploading it in future. So hope you have enjoyed. Don't forget to subscribe our channel if you're liking our content. Thank you very much.